Tonight, we are going to explore the strangest border in all of existence, the place where everything we can possibly know comes to an end. We are taught that space goes on forever. And yet when you look up into the deep night, you do not see an endless ocean of light. You see darkness, a black void between the scattered stars. That darkness has an edge. And when we finally found a way to look at it, the edge was not black at all. It was a faint wall of ancient light, the first light that ever existed, still glowing all around us after nearly 14 billion years. How can the universe have an edge without having a wall? How did two quiet engineers, hunting a strange hiss in a giant horn-shaped antenna, stumble onto the echo of the beginning of time? How could a single faint, pulsing star reveal that the cosmos is far larger than anyone dared believe? And why is the edge of everything not a place at the far end of space, but a moment at the far end of time? These are the questions we will follow, slowly, one at a time, until the darkness overhead begins to look very different to you, and you understand why the edge of all things is racing away from us faster than light itself. If you find the quiet corners of the universe as soothing as we do, you might take a moment to like this video, or to subscribe, so that more calm nights like this one can find their way to you. So settle in, find whatever position feels easiest, and let us begin. Let us begin where every human story begins, by looking up. Imagine yourself lying back on cool grass on a clear, moonless night, far from any city, far from any glowing window. Above you, the sky opens. At first, you see only a handful of stars. Then your eyes adjust, and more appear, and more, until the whole dome of the sky is dusted with faint points of light. It feels infinite. It feels like it goes on forever, for almost all of human history. That is exactly what people believed. The sky was a ceiling of fixed lights, and beyond it lay either the realm of the gods or simply more of the same. Stars without end. But look closely at what is actually there. Between the stars, there is far more darkness than light. The bright points are scattered thin, like a few grains of salt spilled across a black tablecloth. And that darkness is the first clue to one of the deepest puzzles in all of science. If the universe truly were infinite and infinitely old, and if stars truly went on forever in every direction, then every single line of sight you could possibly draw would eventually land on the surface of a star. The whole sky would blaze with light, as bright as the face of the sun, in every direction at once. There would be no night at all. This puzzle has a name. It is sometimes called the dark night sky paradox. And the simple fact that the night is dark, the fact that you can lie on the grass and see black space between the stars, is quietly telling you something enormous. It is telling you that the universe is not infinitely old. It is telling you that there has not been enough time for the light of every distant star to reach you. The darkness is not empty. The darkness is a measurement. It is the universe whispering that it had a beginning, and that beginning was not so very long ago. At least not so very long ago when you measure it against forever. It is a strange comfort to think that the same dark sky has hung over every human who ever lived. The hunters who painted animals on cave walls looked up at it. The first farmers, the builders of every city, the sailors who crossed unknown seas. Every one of them saw very nearly the stars you see tonight, scattered across the very same darkness. The patterns shift so slowly that a single human life cannot notice the change. And all that time, through every one of those nights, the faint glow at the edge of everything was falling just as gently as it falls now, unseen, unsuspected, waiting patiently for someone to grow curious enough to find it. You are simply the latest in a long, quiet line of upturned faces.
So let us draw the picture carefully and slowly. Picture yourself at the center of a vast sphere, not because you are special, not because the universe revolves around you, but simply because of how light and time work. You can only ever see things whose light has had enough time to travel all the way to your eyes. Light is fast, faster than anything else in existence, moving at about 186,000 miles every single second. In 1 second, a beam of light could circle the entire Earth more than 7 times. And yet, even at that staggering speed, light still takes time to cross the gulfs of space. We use that travel time to measure distance. The distance light covers in a single year is called a light year, and it is almost 6 trillion miles. Say that softly to yourself. Almost 6 trillion miles, just to cover 1 year of travel at the fastest speed nature allows. The nearest star to our sun, a small red ember called Proxima Centauri, is more than 4 light years away, which means the light entering your eyes from that star tonight left it more than 4 years ago. You are not seeing the star as it is. You are seeing the star as it was. To look out into space is always, unavoidably, to look back into the past. And so the farther out you look, the deeper into the past you see. The light from the next galaxy beyond our own, the great spiral of Andromeda, has been traveling for about 2.5 million years before reaching you. When that light first set out, there were no humans here to catch it. Our distant ancestors were just learning to shape simple stone tools. The light is a messenger from a time before us, arriving only now. Keep going outward, and the picture grows almost too large to hold. There comes a distance so great that the light leaving an object would need more time to reach us than the universe has actually existed. That light has not arrived. It cannot have arrived. There simply has not been enough time. And so there is a limit, a boundary, not because space stops there, but because our view stops there. We call this boundary the edge of the observable universe. It is the farthest we can ever possibly see. It surrounds us in a perfect sphere, the same distance away in every direction we look. Here the numbers become strange, and I want you to let them wash over you rather than grasp at them. The light that defines this edge has been traveling for nearly 14 billion years. You might think, then, that the edge sits about 14 billion light-years away, but it does not. The edge of the observable universe lies about 46 billion light-years from where you are resting right now.
The whole sphere of everything we could ever see stretches about 93 billion light-years across. The reason for that difference. The reason the edge is so much farther than the age of the light would suggest is one of the strangest and most beautiful facts we will come to tonight. For now, simply let it sit there, glowing softly. The space the light crossed has been stretching the entire time the light was traveling. Inside that sphere is everything. Every star you have ever seen, and every star you never will. Every galaxy, hundreds of billions of them. Each one holding hundreds of billions of stars of its own. Every world, every ocean, every grain of sand on every shore of every planet. All of human history. Everyone who has ever lived and everyone who ever will. All of it floats inside this single bubble of observable space, with you resting quietly near the middle, simply because you are the one who happens to be looking. Now here is where the gentle strangeness begins. We have said the edge of this bubble is the farthest we can see. We have said that beyond it lies darkness, the black void where light has not had time to reach us. So you might expect that edge to be the darkest place of all, a wall of pure nothing. But it is not. The edge is not black. The edge is made of light. It is a soft, smooth, faint glow that fills the entire sky in every direction. A kind of light left over from the very first moments of everything. And the story of how we discovered that glow, how we learned to see the unseeable wall at the edge of the universe, is one of the quietest and most wonderful stories in all of science. It begins not with a telescope pointed at the stars, but with two tired men, a strange antenna, and a hiss they could not explain. But before we meet them, we need to understand the puzzle they were about to solve without even knowing it. We need to understand why the edge of the universe matters, not only to astronomers, but to you, lying here in the dark. Because the question of where everything ends is really the question of where everything began. And the answer to that question is written, faintly and patiently, across the entire sky above your head. For thousands of years, the edge of the universe was a question for philosophers, not for instruments. People asked it the way you might ask a question in a dream. What lies beyond the last star? Is there a wall? And if there is a wall, what lies beyond the wall? The questions chase their own tails, because our minds are built to expect that every place has another place beyond it. We live our whole lives surrounded by edges that are simply borders between one thing and another. The edge of a table, the edge of a field, the shoreline where the land gives way to the sea. In all of these, the edge is just a line, and there is always more on the other side. So when we imagine the edge of the universe, our minds reach for the same picture: a boundary, a barrier, a far wall with something stacked up behind it. And this is the first place our ordinary thinking quietly fails us, because the edge of the universe, as we now understand it, is nothing like the edge of a table. It is not a wall in space at all. It is something far gentler and far stranger. It is an edge in time. To see why this matters to you, and not only to scientists, think of what the answer would tell us. If we can find the true edge, we can read the beginning. The light arriving from the farthest reaches is the oldest light there is.
It carries, written into its faint glow, the conditions of the universe when it was newborn. It tells us how hot everything once was, how smooth, how evenly spread. It tells us the recipe from which every galaxy, every star, every atom in your own body was eventually baked. The iron in your blood, the calcium in your bones, the oxygen filling your lungs as you breathe slowly in and slowly out. All of it traces back to that early furnace. To find the edge is to find our own origin. The most distant thing in the sky is also, in a sense, the most personal. And there are real stakes, too. Beyond the wonder, the way the universe began, and the way it is changing now, decides the way it will end. Whether everything keeps expanding gently forever, growing colder and quieter and more spread out, or whether it might one day slow and stop and fall back together. The edge holds the clue to the fate of all things. That is a heavy thought, so let it be a soft one tonight. The ending, whatever it is, lies so unimaginably far in the future that it cannot touch you here. You are warm. You are safe. The universe is in no hurry, and neither are you. So let us go and meet the two men who, without meaning to, became the first humans ever to detect the edge. The year is 1964. The place is a low green hill in Holmdel, New Jersey, where a great metal horn points up at the sky. This horn is an antenna, but it does not look like the slender antennas you might picture on an old rooftop. It is enormous, a giant scoop of aluminum and steel, shaped a little like an old gramophone, wide enough at its mouth for a person to walk inside and stand up straight. It was built by the telephone company to catch faint radio signals bouncing off early communication balloons in orbit. Now, two young scientists have been given the use of it for pure research, and they intend to listen to the quiet radio glow of our own galaxy. Their names are Arno Penzias and Robert Wilson. They are careful men, patient men, the kind of scientists who measure everything twice and then measure it again to hear the faint whisper of the galaxy. They must first remove every other source of noise from their instrument. Any stray hiss, any background hum would drown out the delicate signal they are after. So they begin, as careful people do, by trying to account for every last bit of static. And almost at once, they run into a problem. There is a hiss, a faint, steady, persistent hiss, a soft static that will not go away. It is there in the morning and there at night. It is there in summer and there in winter. They point the antenna at one part of the sky, and there it is. They swing the great horn to another part of the sky, and there it is again, exactly the same. The hiss comes from everywhere, evenly, in every direction at once, and they have no idea what it is. Now imagine their patience. Imagine the long, quiet hours. They suspect the noise might be coming from the city of New York, glowing with electrical chatter on the horizon. So they point the antenna away from the city. The hiss remains. They wonder if it might be the heat of the antenna itself, the warmth of its own metal parts gently humming. So they chill the equipment and account for every degree. The hiss remains. They wonder if it could be the lingering effect of a nuclear weapons test from a couple of years before. Some echo still ringing in the upper air. They check. That cannot explain it either. The hiss remains. And then they find the pigeons. Inside the great mouth of the horn, a pair of pigeons have made themselves at home. They have built a nest. They have, in the gentle words the scientists later used, coated the inside of the antenna with a white dielectric material, which is to say, the pigeons have left droppings all over the inside of the instrument. Here at last, the men think, is the answer. Surely this mess is the source of the noise. So they catch the pigeons. They clean the antenna by hand, scrubbing every surface until the metal gleams. They even mail the birds away to a distant site, though the pigeons, being pigeons, simply fly back. The men clean again. They seal the seams. They do everything two careful scientists can possibly do. And the hiss remains, faint, steady, even, coming from every direction in the sky. After more than a year of hunting, after eliminating the city, the antenna, the weapons tests, and the birds, Penzias and Wilson are left holding a mystery they cannot shake. There is a soft, uniform glow of radio energy filling the entire sky, and they do not know why. Sit for a moment with how that must have felt. They were not looking for anything grand. They simply wanted a clean instrument. Instead, they had found something that refused to be cleaned away, a whisper soaking through the whole sky. And it was beginning to look as though the whisper was not a flaw in their equipment at all. It was a real signal. It was coming from the universe itself, but they did not yet understand what they had caught. They only knew it was there, patient and everywhere, like a sound you suddenly notice in a quiet room and then cannot stop hearing. What they did not know, what they could not have known, was that only about 30 miles away, at Princeton University, another group of scientists was busy predicting the very thing that Penzias and Wilson had stumbled upon by accident. A physicist named Robert Dicke and his team had reasoned their way to a remarkable idea. If the universe had truly begun in a hot, dense state, then it should still be glowing, ever so faintly, with the leftover warmth of that beginning. They were even building their own antenna to go looking for it. They were, without knowing it, in a quiet race, and they were about to lose it to two men who had not even known there was a race to run. The connection was made by a phone call. Penzias, describing his stubborn, unexplained hiss to another scientist, was told about the Princeton group and their strange prediction. He called Dicke. Dicke listened. And when he hung up the phone, he turned to his colleagues in the room and said, simply, that they had been scooped. The thing they had been preparing to search for had already been found, sitting in the data of two engineers who had spent a year trying to throw it away. The two groups published their findings together, side by side. Penzias and Wilson described the hiss, careful and modest, barely daring to say what it meant. The Princeton group explained what it meant in full. That faint, even glow filling the entire sky was not noise. It was light. It was the oldest light in the universe. The leftover warmth of the beginning of everything.
stretched and cooled by billions of years of travel until it had faded all the way down into the soft radio hum that two patient men kept hearing no matter where they pointed their antenna. We call it the cosmic microwave background, and it is, quite literally, the edge of the observable universe, glowing faintly all around you, even now, even in this room, even in the dark behind your closed eyes. For their discovery, Arno, Penzias, and Robert Wilson received the Nobel Prize in Physics in 1978. Two men who had set out only to clean the static from an antenna had instead found the afterglow of creation. There is something deeply soothing in that, if you let yourself feel it. The greatest discovery did not come from a grand expedition or a flash of genius. It came from patience, from two people refusing to ignore a small thing that did not make sense, and following it gently and stubbornly until it opened into something vast. The edge of the universe revealed itself not to the loudest seekers, but to the most careful listeners. Now we need to slow down and understand what this ancient light really is, and why it reaches us as a soft microwave hum rather than as visible light you could see with your own eyes. To do that, we have to understand the nature of light itself, and the simplest way to picture it is to think of water. Imagine a still pond on a quiet evening. The surface is smooth, like glass. Now picture dropping a small stone into the center. The moment it strikes, a ring of ripples spreads outward, close to the point where the stone fell. The ripples are tight and sharp, packed close together, rising and falling quickly. But as those ripples travel outward across the pond, something happens to them. They spread, they stretch. The distance from one ripple crest to the next grows wider and wider. The waves flatten and soften. By the time they reach the far bank, they may be so gentle and so spread out that you can barely see them at all. The energy is still there. The ripples have not vanished. They have simply been stretched until they fade below what your eye can easily catch. Light behaves in much the same way. Light is a wave, and like the ripples on the pond, light has a distance from one crest to the next. We call that distance the wavelength, and the wavelength is what your eye reads as color. Short, tightly packed waves of light, the ones with crests close together, appear to you as blue and violet. Longer, more stretched out waves appear as red. Stretch them further still, and they slip past the red end of what your eye can see, into a region we call infrared. You cannot see infrared with your eyes, but you can feel a part of it, the warmth you feel from a glowing fireplace. Even without touching it, even with your eyes closed, is infrared light landing softly on your skin. Stretch the waves even further, far past infrared, and you reach the realm of microwaves. These are light waves so long and so gentle and so spread out that they are almost unimaginably faint to our senses. And this is exactly what has happened to the first light of the universe. It began as a fierce, brilliant glow. Light so hot and so energetic that if you could have stood in the early universe,
it would have surrounded you on all sides like the inside of a furnace. But that light has been traveling for nearly 14 billion years. And the entire time it has been traveling, the space it moves through has been stretching, slowly and steadily, in every direction. As the space stretches, it stretches the light waves riding through it, pulling the crests farther and farther apart, just as the ripples spread across the pond. So, the brilliant fire of the beginning has been gently stretched over billions of years, all the way down from blinding light into a faint, cold microwave glow. The fire did not go out. It cooled. It softened. It spread until it slipped entirely out of the range your eyes can see, and settled into the quiet hum that filled the Great Horn antenna in New Jersey. The edge of the universe is not dark because there is nothing there. The edge of the universe looks dark to your eyes only because its light has been stretched past the colors you are able to perceive. Reach out with the right instrument, and the darkness lights up. And it has cooled almost all the way down. When that first light broke free, the universe was glowing at thousands of degrees, as hot as the surface of a star. But across nearly 14 billion years of stretching space, that fierce heat has been drawn out and spread so thin that the glow today carries a temperature of only about 2.7 degrees above absolute zero, which is the coldest anything can possibly be, in the units we use for a winter morning. That is roughly minus 455 degrees Fahrenheit. Far colder than the deepest cold ever felt on Earth. The fire of the beginning has become the faintest imaginable warmth, a whisper of heat soaked evenly into all of space, the same gentle temperature in every direction you could ever turn. It is the softest ember in the universe, and it is everywhere. This is why we build telescopes that can see what the eye cannot. You may have heard of the James Webb Space Telescope, the great golden eye we placed far out in space, 1 million miles from Earth. Its mirror is not built to catch the colors you and I can see. It is built to catch infrared, the stretched out light from the most distant and ancient objects. Light that has been pulled far past red on its long journey to us. Through the eyes of that telescope, the black void is not so black. It fills with the faint glow of galaxies so far away and so long ago that their light left them when the universe was very young. Webb can peer almost all the way back, almost to the beginning, gathering the soft infrared embers of the first galaxies that ever formed. But even Webb cannot see the very edge. Even Webb, with all its patience and all its precision, reaches a point beyond which there are no galaxies to see, because before that moment in time, no stars and no galaxies had formed yet. Beyond the farthest galaxy lies a time when the universe was simply a glowing fog. And the light from that glowing fog is the cosmic microwave background. It is not the light of any star. It is older than every star. It is the light of the universe itself. From before there was anything in it but light and heat and the smooth, even soup of the beginning. To understand where that soup came from, we have to leave the antenna on the hill and travel back a few decades to meet some of the people who first realized that the universe was not the calm, fixed, eternal place everyone had always assumed it to be. because before anyone could understand the edge, someone first had to discover that the universe was moving, that it was growing, that it had a history. The story really opens in the early years of the 20th century, in a place you might not expect, not at a great telescope, but at a desk piled with photographic plates, in the hands of a woman named Henrietta Leavitt. She worked at the Harvard College Observatory, in a room full of women who were employed to study the night sky as it had been captured on glass plates, measuring and cataloging the brightness of thousands upon thousands of stars. The work was painstaking and quiet and largely uncredited. The women who did it were not even allowed to operate the telescopes. They were given the photographs and the numbers, and they were expected simply to measure. But Henrietta Leavitt, measuring star after star with extraordinary care, noticed a pattern that no one else had seen. She was studying a particular kind of star that does not shine steadily, but pulses, slowly brightening and dimming and brightening again in a regular, repeating rhythm, like a chest rising and falling in calm sleep. These stars are called Cepheid variables. And what Leavitt discovered, hidden in her careful measurements, was a beautiful and powerful rule. The slower a cepheid pulses, the brighter it truly is. The rhythm of its pulsing reveals its real, underlying brightness. Take a moment to feel why that is such a gift. Out in space, a star can look dim for two completely different reasons. It might be a faint star nearby, or a brilliant star very far away. From a single point of light, you cannot tell which. But if you can measure how truly bright a star actually is, and then compare that to how dim it merely appears to be, the difference tells you exactly how far away it must be. A bright thing that looks faint must be distant, and you can calculate just how distant. Leavitt had handed astronomy a measuring stick that could reach across the heavens. She had given us a way to measure the true distance to the stars. She did not live to receive a prize for it. She died before the full power of her discovery was understood. But every map of the universe we have ever made rests quietly on the rule she found at that crowded desk in Harvard, measuring points of light on glass. A few years later, that measuring stick found its way into the hands of a man named Edwin Hubble, working at the Mount Wilson Observatory in California, where a great telescope with a mirror 100 inches across stared out at the night. In the middle of the 1920s, one of the biggest questions in all of astronomy was deceptively simple. Those faint, fuzzy, cloudy smudges scattered across the sky, the ones that did not look like sharp points of starlight, but like little patches of mist. What were they? The word for them was nebula, which simply meant cloud. And the common assumption was that they were exactly that, clouds of glowing gas and dust floating among the stars of our own galaxy. In that picture, our galaxy was the whole universe, one great island of stars, and there was nothing beyond it. And the largest and brightest of these fuzzy patches was a great oval glow in the constellation Andromeda. Hubble pointed the 100-inch telescope at Andromeda night after night, and he searched for one of Henrietta Leavitt's pulsing stars hidden inside it. And he found one. He watched it brighten and dim, and he timed its slow rhythm. From that rhythm, using Leavitt's rule, he could read the star's true brightness, and then he compared that to how faint the star appeared through his telescope. The answer that came back was almost impossible to believe. The star was so far away that it could not possibly lie inside our own galaxy. It was far, far beyond it, which meant that Andromeda was not a cloud of gas among our stars at all. It was a whole separate galaxy, a vast island of hundreds of billions of stars of its own, drifting at an unthinkable distance across the dark. In a single measurement, the universe became almost incomprehensibly larger than anyone had imagined. Our galaxy was not the whole of creation. It was one island among countless others. The fuzzy smudges in the sky were not clouds. They were other galaxies scattered to the edge of sight. That alone would have been enough to rewrite every textbook. But Hubble was not finished. And the next discovery was stranger still. He had a colleague, a quiet and meticulous astronomer named Vesto Slipher, who had spent years patiently capturing the light of these distant galaxies and spreading it out into its colors, the way a prism spreads sunlight into a rainbow. And Slipher had noticed something curious about almost all of them. The light from nearly every distant galaxy was shifted. Its colors were pushed toward the red, stretched toward longer wavelengths, as though every one of these galaxies were sliding away from us through space. To understand what that shift means, you do not need any physics at all. You only need to have stood by the side of a road as an ambulance rushed past. Listen, in your memory, to the sound of its siren. As the ambulance races toward you, the pitch of the siren is high and tight. And the instant it passes and begins to speed away, the pitch drops, falling lower and stretching out. The sound itself has not changed. What changes is the spacing of the sound waves. As the ambulance approaches, each pulse of sound is launched from a little closer than the last, so the waves bunch together and the pitch rises. As it departs, each pulse comes from a little farther away, so the waves stretch apart and the pitch falls. This gentle effect, this rising and falling with motion, is called the Doppler effect. And once you have heard it, you can never unhear it. Light does the very same thing. When something glowing moves away from you, the light waves it sends stretch out, and the color shifts toward the red. When it moves toward you, the waves bunch up, and the color shifts toward the blue. We call the stretching a redshift. And what Slipher and Hubble found, looking out at galaxy after galaxy, was that almost all of them were redshifted. Almost all of them were moving away. Wherever they looked, the galaxies were receding, sliding off into the dark in every direction. And then came the deepest pattern of all, the one that changed everything. Hubble compared how far away each galaxy was, using Leavitt's measuring stick, with how fast it was rushing away, using the redshift, and he found a clean and simple relationship hiding in the data. The farther away a galaxy was, the faster it was fleeing. A galaxy twice as distant was running away twice as fast. A galaxy 10 times as distant was running away 10 times as fast. The whole universe, in every direction, was flying apart. and the most distant pieces were flying apart the fastest. Now sit gently with what that means, because at first it sounds as though it makes us the center of some great explosion, with everything blowing away from us in particular. But that is not the picture at all. And the truth is far calmer and far stranger. Imagine a loaf of raisin bread rising slowly in a warm oven. The dough is studded with raisins, scattered all through it. As the dough rises, it swells in every direction at once. Pick any single raisin and pretend you are sitting on it. You will see every other raisin moving away from you, because the dough between you and each of them is expanding, and the raisins farthest away will appear to move away fastest, because there is more swelling dough between you and them. Every raisin sees the same thing. No raisin is the center. The expansion is happening everywhere, all at once, throughout the whole loaf. This is the heart of it. The galaxies are not flying through space away from some central point. Space itself is expanding, swelling gently in every direction, carrying the galaxies along with it like raisins in rising dough. There is no center. There is no place where the expansion began that you could point to and say, "It started here." It is happening at every point, including the point where you are resting right now. The space between you and the farthest galaxies is quietly, patiently growing, even tonight, even in the time it takes you to draw one slow breath. This was the discovery that broke the old, comfortable belief in a fixed and eternal universe, and it placed a strange and wonderful problem at the feet of the greatest physicist of the age, because just a few years earlier, Albert Einstein had built a magnificent new theory of gravity, his theory of general relativity, finished in 1915. It was, and still is, one of the most beautiful descriptions of nature ever written. It explained gravity not as a mysterious pull, but as the bending and curving of space itself around anything that has mass. And when Einstein used his own equations to describe the entire universe, they told him something he was not prepared to believe. His equation said the universe could not be standing still. They insisted it must be either expanding or contracting, growing or shrinking, but never simply sitting there, fixed and unchanging. And Einstein, like nearly everyone else of his time, was certain the universe was eternal and still. So he did something he would later regret. He reached into his beautiful equations and added a new term, a kind of pushing force woven into empty space itself, finely balanced to hold everything in place against the inward pull of gravity. He called it the cosmological constant. It was a quiet fudge, a way to force his equations to describe the calm, static universe he expected to find. And then Hubble showed that the universe was not static at all. The galaxies were flying apart. The expansion was real. Einstein's original equations, the ones that had told him the universe must be moving, had been right all along, before he overruled them. He had let his expectation override his own mathematics. He is said to have called the cosmological constant the greatest blunder of his life. And he removed it, embarrassed that he had not simply trusted what his equations had tried to tell him. There is a lesson there as gentle as it is humbling. The universe will tell you what it is. If only you are willing to listen instead of insisting. Even the greatest mind of an age can be led astray by being too sure of the answer in advance. But here is one of the loveliest twists in the whole story, and we will return to it later tonight, so simply tuck it away for now. Einstein was wrong about the static universe, but he may not have been wrong about the cosmological constant, that quiet pushing force in empty space. The one he invented and then threw away in shame would return, decades later, in a form no one expected, and it would turn out to be one of the deepest mysteries in all of science. Sometimes a mistake is only an answer arriving far too early. Once the universe was known to be expanding, a beautiful and simple idea followed, and it came from a quiet Belgian priest and physicist named Georges Lemaitre. He reasoned in the most natural way. If everything is flying apart now, if every galaxy is drifting away from every other, then long ago everything must have been closer together. And if you imagine running the whole great film of the universe backward, the galaxies would draw nearer and nearer, the space between them shrinking, the whole cosmos growing hotter and denser and smaller, until you arrive at a single moment when everything we can see was packed into an unimaginably small, hot, dense state. Lemaitre called it the primeval atom. We know it today by a more famous name, the Big Bang. But here we meet one of the most common and most misleading pictures in all of popular science. And tonight we are going to set it gently aside. Most of us were taught, as children, that the Big Bang was an explosion, a tiny dot of infinite density, sitting in the middle of empty space, that detonated like a bomb and flung all the matter of the universe outward into the surrounding void. It is an easy picture to hold. It seems to make sense. If everything is rushing apart now, then surely it all blew out from one point. But that picture is wrong, and letting go of it is one of the keys to understanding the strange edge we are chasing tonight. The Big Bang was not an explosion in space, because there was no surrounding space for it to explode into. The Big Bang was the beginning of space itself. It did not happen at one location, with everything else watching from outside. It happened everywhere, all at once, throughout the entire universe. Because at that moment, the entire universe was that hot, dense state. There was no outside. There was no empty room with a firecracker going off in the corner. Every point that exists today, including the exact point where your body now rests, was part of that beginning. The Big Bang happened here, in this room, as much as it happened anywhere, because every place was the same place when everything was packed together. Go back to the raisin bread, but now imagine the dough so compressed that there is almost no space between the raisins at all. Then let it begin to swell everywhere at once, every tiny region of dough expanding away from every other. That is closer to the truth. The expansion is not matter rushing outward through space. It is space itself coming into being and stretching everywhere, all together. We do not know how large the universe was at that first instant. It may have been small. It may even have been infinite already, simply far denser everywhere than it is now. But what we are fairly confident of is that in the tiniest sliver of a second,
far less than the blink of an eye. The universe expanded with breathtaking speed. A region smaller than a single grain of sand could have swelled to something the size of a galaxy in less time than it takes light to cross the width of an atom. This sudden, enormous early swelling has a name. It is called inflation. And though it lasted only the faintest flicker of a moment, it set the smooth, even stage on which everything else would slowly unfold. Now follow the cooling, because this is where the edge of the universe is finally born. In the first moments, the universe is unthinkably hot, far too hot for any atom to exist. It is a blazing fog of the smallest particles, packed so tightly and moving so violently that light itself cannot travel freely. Picture trying to see across a dense morning mist, where every beam of light is scattered the instant it sets out, bouncing off droplet after droplet, never reaching your eye. In the early universe, light could not travel in a straight line at all. It was endlessly scattered by the seething particles. The entire universe was glowing, but it was opaque, a wall of fog with no clear path through it. And then the universe cooled. As space expanded, it stretched and thinned and cooled the fiery soup gently, steadily, over thousands of years. And at last, when the universe was about 380,000 years old, it crossed a quiet threshold. It became cool enough for the particles to settle down and join together into the first complete atoms. The fog cleared. Suddenly, for the first time, light could travel freely across space without being scattered. In a single great moment, all across the universe at once, the cosmos became transparent, and the light that had been trapped in the fog was set free to fly. That light is the cosmic microwave background. That moment, 380,000 years after the beginning, is the oldest thing we can ever see. We cannot see before it, because before it, the universe was an opaque fog, and no light could reach us from within it. We can only see as far back as the moment the fog cleared. Astronomers have a lovely, gentle name for that moment. They call it the surface of last scattering. It is the last place the ancient light bounced before it began its long, quiet journey toward your eyes. And that surface, that final clearing of the fog, is the true edge of the observable universe. It surrounds you in every direction, the same distance away no matter where you look, a vast sphere of softly glowing first light. Here is the part that I want you to let settle over you slowly, like a blanket. The edge of the universe is not a place. It is a time. When you look out at that faint microwave glow filling the sky, you are not looking at a distant wall standing somewhere out in space. You are looking back at the universe as it was when it was only 380,000 years old, a newborn, still glowing from its own first warmth. The edge is the past. It is the boundary not of where we can travel, but of how far back we can see. And the reason it forms a perfect sphere around you is the same reason any horizon is a circle around the one who stands at its center. You are simply looking back the same distance in every direction, and the same distance back means the same distance in time. And now we can finally answer the strange riddle we left glowing at the very beginning of tonight. We said the light of this edge has been traveling for nearly 14 billion years, and yet the edge itself lies about 46 billion light years away.
How can light that has traveled for 14 billion years now be sitting 46 billion light years from us? The answer is the expansion of space, the same gentle swelling we have been speaking of all along. When that ancient light first set out toward us, the place it came from was far closer than 46 billion light years. It was, in fact, quite near. But the entire time the light was crossing the gulf toward us, the space it was traveling through was stretching, carrying its destination farther and farther away, like a moving walkway running gently backward beneath a slow walker. The light kept moving toward us at its steady speed, but the ground it had already crossed kept lengthening behind it, and the ground ahead kept growing too. By the time the light finally arrived at your eyes tonight, the spot it originally left has been carried by the patient expansion of space, all the way out to about 46 billion light years away. The light did not travel 46 billion light years. It traveled for nearly 14 billion years through space that would not hold still. And this leads us into the strangest fact of the whole night, a fact so odd that when people first hear it, they are sure it must be a mistake. The expansion of space can carry distant things away from us faster than the speed of light. You have surely heard that nothing can travel faster than light. That is one of the firmest rules in all of physics. And it is true. No object, no star, no spaceship, no particle can move through space faster than light. But the rule is about moving through space. It says nothing about space itself. And space itself is allowed to stretch as fast as it likes, by as much as it likes, with no speed limit at all. So picture two galaxies, very far apart, each one sitting still in its own patch of space, neither of them traveling anywhere. Between them lies an enormous gulf of space, and all of that space is gently expanding, every tiny piece of it swelling a little. Add up all that swelling across such a vast distance, and the two galaxies find themselves drawn apart faster than a beam of light could cross between them. Neither galaxy is breaking the speed limit, because neither is moving through space at all. It is the space between them, growing everywhere at once, that carries them apart. The rule is never broken. The galaxies simply rest in place, while the distance between them grows and grows. This is why the observable universe has an edge in the first place, and why that edge is forever beyond our reach, out past a certain distance. Space is expanding so quickly that light leaving a galaxy out there can never close the gap to us. It sets out toward us, but the space ahead of it stretches faster than it can cross, and so it never arrives. There are galaxies whose light is, in this very moment, trying to reach us and failing, falling forever behind the swelling tide of space. We will never see them as they are now. We will only ever see the old light they sent long ago, before the expansion grew too swift. The edge of the observable universe is the line beyond which the universe is running away from us, faster than its own light can travel. And now we come back to Einstein's discarded mistake. The cosmological constant, the pushing force he was so ashamed of inventing. For most of the 20th century, astronomers believed the expansion of the universe must be slowing down. It seemed obvious. The galaxies all pull on one another through gravity, and gravity always pulls things together. So surely, over the long ages, gravity should be quietly putting on the brakes, slowing the great expansion bit by bit, perhaps even one day halting it and drawing everything gently back together. To find out how fast the expansion was slowing, two teams of astronomers set out in the 1990s to measure it as precisely as they could. They used a particular kind of exploding star, a type of supernova that always burns with very nearly the same true brightness, like a standard candle placed far out in the dark. By measuring how faint these distant explosions appeared, they could tell how far away they were, and by reading their redshift, they could tell how much the universe had expanded since the light left them. In 1998, both teams, working separately, arrived at the same impossible answer. The expansion of the universe was not slowing down at all. It was speeding up. The galaxies were not gently coasting to a stop. They were accelerating apart, faster and faster, as though some hidden force were pushing them outward against the inward pull of all their gravity. Take a moment to imagine the quiet shock of that. They had set out to measure the rate of slowing, fully expecting to confirm what everyone believed. Instead, they found the opposite, and the result was so strange that they spent a long time doubting their own data, checking every step, looking for the error that surely must be there. But there was no error. The acceleration was real, and the force driving it had no name and no explanation. We call it dark energy, which is really just an honest way of admitting we do not know what it is. It is the energy of empty space itself, a faint pushing pressure woven into the vacuum, growing stronger as the universe grows larger. Because the more empty space there is, the more of this strange energy there is to push. And this brings Einstein's old blunder all the way back around, the cosmological constant. That pushing force in empty space that he invented and then threw away in embarrassment turns out to look remarkably like the dark energy that is accelerating the universe today. He had the right idea for the wrong reason at the wrong time. He imagined a pushing force to hold the universe still. The real pushing force does the opposite. It drives the universe ever faster apart. But the term he added to his equations, the quiet pressure of empty space, was real after all. For the discovery of this acceleration, 3 of the astronomers who measured it received the Nobel Prize in Physics in 2011. And the deepest part of their discovery is that most of the universe, very nearly 3/4 of everything there is, appears to be made of this dark energy we cannot see, cannot touch, and do not understand. The thing that fills the most of the cosmos is the thing we know the least about. There is a strange and gentle humility in that. We have mapped the edge of everything we can see, and discovered that most of reality remains a mystery we have only begun to name. There is one more chapter to this story before we gather it all together, and it is perhaps the most tender of all, because it is the chapter where we learn to see the edge not just as a hiss, but as a picture. After Penzias and Wilson first caught the faint glow, scientists wanted to map it. They wanted to know whether the ancient light was perfectly smooth in every direction, or whether it carried faint markings, gentle patches slightly warmer here and slightly cooler there. So they built spacecraft, careful and patient, and sent them out beyond the warm interference of the Earth to gaze at the whole sky at once and measure the temperature of the first light to an extraordinary fineness. The first of these, a satellite launched in 1989, confirmed something beautiful. The glow is astonishingly smooth, the same temperature in every direction to better than 1 part in many thousands. The leftover warmth of the beginning spread out almost perfectly evenly across the entire sky. It is one of the smoothest things in all of nature, but it is not perfectly smooth. And that tiny imperfection is the whole reason you exist. Hidden in the glow are faint ripples, regions that are the merest fraction of a degree warmer or cooler than their surroundings. These ripples are a map of the newborn universe, a baby picture of everything, taken when the cosmos was only 380,000 years old. The slightly denser patches, the faintly cooler spots, were places where matter was very gently more crowded than elsewhere. And over the long ages that followed, gravity went quietly to work on those tiny crowds. Where there was a little more matter, gravity pulled in a little more, and then a little more, slowly, patiently, over hundreds of millions of years, gathering the gentle ripples into clumps, and the clumps into clouds, and the clouds into the first stars, and the stars into the first galaxies. Every galaxy in the sky tonight, including our own, grew from one of those faint, warm, or cool patches in the first light. The map of the newborn universe is the seed map of everything that would ever be. When we photograph the cosmic microwave background with all its delicate modeling, we are looking at the blueprint from which every star and every world, including this one, was slowly drawn. Later spacecraft made the picture sharper and sharper, until we had a map of the entire sky at the dawn of time. Every faint ripple measured and recorded, the oldest photograph ever taken. And from that single image, scientists could read the deep properties of the whole universe, its age, its composition, how much ordinary matter it holds, how much dark matter, how much of that strange dark energy, the proportions of everything, written into the gentle pattern of the first light. An entire universe described from the faint warmth of its own first morning. And what lies beyond that edge, beyond the surface of last scattering, beyond the farthest glow we can ever map. Here we reach the honest limit of all our knowing, and there is a deep peace in arriving at it. We do not know. We cannot know. Not from here. Because no signal of any kind can reach us from beyond that boundary. The universe almost certainly continues on past the edge of what we can see, perhaps far beyond, perhaps without end. The observable universe is not the whole universe. It is only the part whose light has had time to find us. There may be countless galaxies out past the edge, whole oceans of them, that we will never glimpse, because the space between us is growing faster than their light can cross. They are real, and they are there, and they are forever beyond our sight. The edge is not the end of everything. It is only the end of everything we can see. And to stand at that boundary, and to know that more lies beyond it that we can never reach is not a sadness. It is a reminder of how gently large the world is, how much of it asks nothing of us, how much of it simply is, out there in the calm dark, whether we ever know of it or not. So let us gather, slowly and gently, the strange things we have learned about the edge of the universe, one at a time, the way you might set smooth stones in a row along a windowsill. There is no need to hold them all. Just let each one rest in your mind for a moment before the next. The first strange thing we find is that the edge is not made of darkness, but of light. Everything in our ordinary experience tells us that the farthest reaches should be the emptiest and the blackest. Instead, the boundary of all we can see is a soft, even glow, the cooled and stretched remains of the universe's first light, filling the whole sky in every direction. The darkness you see between the stars at night is only the part of that glow your eyes cannot read. The edge is not a void. The edge is luminous. We were simply not built to see it. The second strange thing we find is that the edge is not a place at all, but a time. We naturally imagine the boundary of the universe as a far wall standing somewhere out in space. But there is no wall, and there is no somewhere. When you look toward the edge, you are looking backward into the deep past, toward the moment the universe was only 380,000 years old and first became clear enough for light to travel. The edge is the oldest thing we can see, and it surrounds us only because, in every direction, we are looking back the same distance in time. The third strange thing we find is that the edge is far more distant than the age of its light should allow. The glow at the edge has been traveling for nearly 14 billion years. And yet, the place it came from now rests about 46 billion light-years away. Space did not stay still while the light crossed it. The whole time the ancient light was traveling toward us, the space it moved through was stretching, pushing its origin steadily farther away. The light traveled for a certain span of time, but the distance it seems to have covered has been quietly multiplied by the growth of space itself. The fourth strange thing we find is that distant galaxies are racing away from us faster than light, without breaking any law of nature. Nothing can move through space faster than light, but space itself has no speed limit. And across vast enough distances, the gentle swelling of space adds up until faraway galaxies are carried apart faster than any beam could cross between them. They are not moving. They are sitting still while the space beneath them grows. The rule is never broken. The distance simply outraces the light. The fifth strange thing we find is that the Big Bang did not happen in one place. It was not an explosion in the middle of empty space, hurling matter outward into a surrounding void. It was the beginning of space itself, happening everywhere at once. Every point that exists today was part of that beginning, including the very spot where you are resting now. The Big Bang did not happen far away and long ago in some distant corner. It happened right here, as much as anywhere, because here and there and everywhere were the same single place when all of it was packed together. The sixth strange thing we find is that the expansion of the universe is not slowing down, as everyone long believed, but speeding up. For most of a century, scientists were certain that gravity must be quietly applying the brakes, drawing everything back together over the ages. Instead, the galaxies are accelerating apart, driven by a hidden pressure in empty space that grows stronger as the universe grows larger. The universe is not coasting gently to a stop. It is opening faster and faster, like a flower that never finishes blooming. And the seventh strange thing we find is the gentlest and most humbling of all. The thing that fills the most of the universe is the thing we understand the least. Nearly 3/4 of all there is appears to be this dark energy, the pushing pressure of empty space. And we do not know what it is. We have charted the boundary of everything we can see, traced it back to the first moment of light, measured its temperature to a fraction of a degree, and at the end of all that careful work we are left standing before a vast and patient mystery. We have learned enough to know how much we still do not know, and that, far from being a defeat, is one of the quietest joys of looking up at all. Now you might wonder, lying here in the warm dark, why any of this should matter to an ordinary life. The edge of the universe is so impossibly far away. The numbers are so large they stop meaning anything. What does the cooled glow of the beginning have to do with you? Here, tonight, beneath your blanket. And the answer is closer and softer than you might expect. It matters because that ancient light is your own beginning, written across the whole sky. The smooth, even glow at the edge of the universe is a portrait of the simple, formless soup from which everything you have ever known slowly emerged. In that early warmth, there were no stars, no planets, no atoms heavier than the lightest few. Everything else, every heavier element, was cooked later, inside the hearts of stars and in the violent deaths of stars, and then scattered out into space to gather again into new worlds. The carbon in your cells, the iron carried in your blood, the calcium holding up your bones as you lie here breathing. Every bit of it was forged in stars that lived and died long before the earth existed. When you look at the edge of the universe, you are looking at the smooth, undivided beginning from which you and everyone you love were eventually drawn. You are quite literally made of the aftermath of that first light. It matters because it tells us, with great patience and great gentleness, that the universe is not fixed and finished, but unfolding. It had a beginning. It has a history. It is changing even now, expanding a little more with every breath you take. And it will keep changing long after this night, this year, this whole age of the world has passed. You are living inside a story that is still being told, a story so vast that your entire life is a single soft syllable within it. And there is comfort in that smallness, if you let there be. The weight you carry, the worries that feel so large at the end of a long day, all of it is held inside something so enormous and so calm that it can absorb any trouble without the slightest strain. The universe has room for all of it, and more. And it matters because of what the whole long search reveals about us. The small, brief, curious creatures doing the looking. Think of the chain of quiet people who brought us this picture. A woman measuring points of light on glass plates, uncredited, patient, finding a rule that would reach across the heavens. A man comparing the slow pulse of a single far star, night after night, until our galaxy quietly became one island among billions. A priest reasoning his way backward to the first moment. A great physicist humble enough, in the end, to let the universe correct him. Two engineers refusing to ignore a hiss they could not explain, following it gently until it opened into the afterglow of creation. None of them set out to conquer anything. They simply paid close attention, and they were willing to be surprised. That is the whole of it. That is how we came to know the edge of everything, not by force, but by patience, not by certainty, but by a willingness to look and listen and be amazed. Let us pause here, in the middle of the deep night, and simply rest in the wonder of it for a moment. There is something almost unbearably tender about the fact that the universe keeps a memory of its own beginning, and that the memory is still arriving, still washing over us, gentle and faint and everywhere. The first light has been traveling toward this moment for nearly 14 billion years. It set out when there were no stars, no planets, no eyes anywhere to receive it. And it has been falling silently through the growing dark all this time, crossing an ocean of space that would not stop widening beneath it, only to arrive at last in an age when, on one small blue world, creatures had finally grown curious enough and patient enough to build instruments that could feel it. The light did not know we were coming, and yet here we are, exactly in time to catch it. We happen to live in a remarkable window, because the universe is expanding, and that expansion is speeding up. The distant galaxies are slowly slipping away from us, one by one, carried beyond the edge of what we can ever see, far in the future, unimaginably far, so distant that the number of years has no real meaning. The sky will be emptier than it is tonight. The galaxies beyond our own small neighborhood will have receded so far and so fast that their light will no longer reach across the widening gulf. A creature looking up from some distant world in that far future would see only its own local cluster of stars, surrounded by a darkness that gives no hint of the vast cosmos that once lay beyond. The very evidence of the expanding universe, the red-shifted galaxies, the glow at the edge would be gone, faded past the horizon, carried away by the same gentle swelling we have been speaking of all night. Which means that we, here, now, in this particular age of the universe, are among the lucky ones. We can still see the galaxies. We can still catch the first light. We can still read the story of the beginning, written plainly across the sky, because we arrived while the writing is still legible. There will come a time when it cannot be read at all, but that time is not now. Now the sky is full. Now the ancient glow still reaches us. Now, tonight, The whole vast story is still ours to hold, if only for a little while. There is a quiet privilege in simply being here to look, in this brief, bright window when the universe is still willing to show us where it came from. And there is a deep peace, too, in how slowly all of this unfolds. Everything we have spoken of tonight happens on time scales so enormous that they move beneath our lives like the turning of the seasons beneath a single afternoon. The galaxies drift apart over billions of years. The light cools over billions of years. The far future of an empty sky lies so distant that the entire history of the human race, every empire and every song and every life, is less than a single heartbeat against it. You do not have to do anything about any of it. You could not if you tried. It will all unfold in its own slow time, with or without your worry, gently, patiently, exactly as it has for nearly 14 billion years. There is nothing to fix tonight. There is nothing to carry. The universe is vast and old and calm, and it is holding everything, including you. So now, with the night grown deep around you, let us go back to the beginning and tell the whole story once more, softly and simply, so that you can let every piece of it drift away. There is nothing left to learn. You can stop holding the names and the numbers now. Just let the shape of the story carry you, the way a slow current carries a leaf. It begins with darkness, with a human being lying on the cool grass on a clear night, looking up and seeing far more black sky than stars, and that simple darkness, that quiet emptiness between the few scattered lights, was the first clue that the universe is not infinite and eternal, but had a beginning, not so very long ago, against the scale of forever. It begins with light and how it travels, with the understanding that to look out into space is always to look back into time, because light needs time to cross the great gulfs. And so the farther we look, the deeper into the past we see, until we reach a distance so great that no light has had time to arrive. And there, all around us, lies the edge of everything we can ever see, the same far distance away in every direction. It begins with two patient men on a green hill in New Jersey, listening to a hiss they could not explain. A soft, even static coming from every part of the sky at once. They blamed the city and the antenna, and even the pigeons nesting in the great horn. They cleaned and checked and cleaned again, and still the hiss remained. Until at last they understood that it was not noise at all. It was the oldest light in the universe, cooled and stretched into a faint microwave glow, the afterglow of the beginning, filling the whole sky and falling softly all around them. It begins with a woman measuring stars on glass plates, who found that certain pulsing stars reveal their true brightness through the rhythm of their pulse, and so handed us a measuring stick that could reach across the heavens. And with a man who used that stick to discover that the faint fuzzy patches in the sky were not clouds among our stars, but whole separate galaxies, vast islands of stars unthinkably far away, scattered out to the edge of sight. It begins with a shift in color, the gentle reddening of the light from almost every galaxy, telling us they are all sliding away from us.
and the farther ones sliding away faster, like raisins drifting apart in a slowly rising loaf of bread. Not flying through space from some central blast, but carried apart by space itself, swelling gently in every direction, with no center anywhere, the expansion happening at every point at once, including the very point where you now rest. It begins with running that expansion backward, until everything draws together into a single hot, dense beginning that we call the Big Bang, which was not an explosion in space, but the beginning of space, happening everywhere at the same moment, with a young universe so hot it was an opaque fog, until it cooled enough, about 380,000 years in, for the fog to clear and the trapped light to fly free at last. And that freed light, stretched and cooled across the ages, is the glow at the edge, the surface of last scattering, the oldest thing we can ever see, surrounding us not as a wall in space, but as a boundary in time. And it ends, for now, with mystery, with the discovery that the expansion is speeding up, driven by a dark energy in empty space that we still cannot explain, the very thing the greatest physicist of the age once invented and then threw away in shame. With the humbling truth that most of the universe is made of something we do not understand, and with the quiet wonder that we, small and brief as we are, came to know any of this at all, simply by paying close attention and being willing to be surprised. Before we let the night carry you all the way down into sleep, here is one last gentle thought to hold, and then you can release even this. That ancient light, the glow at the edge of the universe, is not only out there at the far reach of the sky, it is here. It is everywhere. It passes through this room right now, through the walls, through the air, through you. A faint and constant rain of the oldest light there is, falling softly on everything, all the time. There is no place you can go to escape it, because it fills all of space evenly. The leftover warmth of the beginning soaked into every corner of the cosmos. In the days of older televisions, the kind with rounded glass screens that hummed when you turned them on, you could tune to a channel with no station and see a flickering snow of static, and hear a soft, rushing hiss. And a small part of that snowy flicker, a tiny share of that gentle hiss, was the cosmic microwave background itself, the same ancient glow that filled the Great Horn antenna in New Jersey, arriving in ordinary living rooms, falling onto ordinary screens, watched by people who had no idea they were looking at the afterglow of the beginning of time. The edge of the universe has been quietly visiting us all along, in the soft snow between the channels, in the faint warmth in the empty sky, patient and everywhere, asking nothing, simply present. Think, as you drift, of the sheer scale of what holds you. Our sun is one star among several 100 billion stars in our galaxy. Our galaxy is one among perhaps 2 trillion galaxies scattered through the observable universe. If you tried to count the stars at a rate of 1 every second, you would not finish a single galaxy in 1,000 lifetimes. And all of it, every star and every galaxy and all the dark space between, floats inside that one great sphere, about 93 billion light-years across. with the soft glow of the first light gleaming faintly all around the rim. It is too large to picture. You are not meant to picture it. You are meant only to rest inside it, a small, warm point of life near the center of an unimaginable calm.
And that is enough. That is the whole of it. You have come a very long way tonight. You have traveled out past the last star, to the edge of everything we can see. And you have found that the edge is not a wall, but a soft glow, not a place, but a moment, not an ending, but a beginning, the first light of the universe still falling all around you. There is nothing more to understand now. There is nothing left to hold. So let it all begin to drift away. Let the numbers go first, the billions of light years and the billions of years, all of them loosening their grip, floating off into the dark like sparks rising from a fire. Let the names go too, the careful listeners and the patient measurers. They have done their work, and you can set them gently down. Let the whole great picture soften at its edges and dissolve until there is nothing left to think about at all. Only the quiet, only the warmth, only the soft and even glow that asks nothing of you. Feel how heavy your body has become against the bed. Feel the weight of your arms, your legs, sinking down, held and supported. Nothing for them to do. Let your shoulders fall away from your ears. Let the small muscles of your face go loose and soft, your brow smooth, your jaw unclenched, the corners of your eyes at rest. Let your breathing slow, all on its own, in and out, like a gentle tide drawing up ashore and slipping back again, without any effort from you at all. In and out, slow and soft and easy. There is nothing to carry now. The day is over, and it is done, and you do not have to hold any of it any longer. Whatever was left undone can wait. Whatever was difficult can rest. You are here, warm and safe, held by the bed beneath you and by the vast and patient universe beyond it, the one that has been expanding gently for nearly 14 billion years and will keep on, slow and calm, long after this night has passed. It is in no hurry. There is nowhere it needs to be, and neither do you. The light is still falling, soft and even, the oldest light there is, the warmth of the beginning still arriving after all this time. It does not need you to watch it. It will keep falling while you sleep, all through the night, all around you, the way it has fallen through every night that has ever been. You can let your mind go quiet now. You can let the last thoughts drift apart like distant galaxies, slipping gently beyond the horizon, growing fainter and farther and softer until they fade into the calm dark. There is nothing to do. There is nothing to remember. There is only the slow rise and fall of your breath, and the deep stillness all around you, and the faint warm glow of the first light, holding you the way it holds everything, gently, evenly, forever. Rest now, sleep deeply, and let the gentle dark hold you until morning.